Hello everyone. In this video, we are going to see the types of element, convergent requirement of the displacement function in unit number 6, finite element method for the subject structural analysis 2. So first we see the types of elements. The first type is 1D elements. So here, the different types of 1D elements are two noded bar element. So a single bar, the two nodes are considered 1 and 2. So as it is one dimensional, so there will be 1 degree of freedom at each node. So as there are two nodes, so total degree of freedom is equal to 2. So if you see a bar element which is having the three nodes, so at each node there is 1 degree of freedom. So total number of nodes are 3. So 3 into 1, it is equal to 3. So degree of freedom for 3 noded bar element is equal to 3. Then the next one dimensional element is a beam element. So in beam element, we know that there will be a displacement in y direction and also there will be a rotation at each joint, at each node. So at each node there will be a 2 degree of freedom. So there are two nodes, so 2 into 2, 4. So degree of freedom for the beam element is equal to 4. So the second element is the two-dimensional element. So as in one-dimensional element, at each node there was 1 degree of freedom. Okay. So in two-dimensional element, at each node there will be a 2 degree of freedom. So if you see, the first element is a triangular element. Okay, so for this triangular element there are three nodes. So at each node there will be a displacement in y direction, so which we called as v1. Second one is u1. Second one, for node 2, again there will be displacement in y direction, displacement in x direction. Okay, we see the node 3. So again there will be displacement in x direction and y direction and displacement in x direction. So here displacement in x direction we call it as u1, displacement in y direction we call it as v1. So there are three nodes, at each node 2 degree of freedom. So total number of degree of freedom for a triangular element is equal to 6. Okay. Now the next example is the rectangular element. Okay. So for rectangular element there are 4 elements. So again there will be a displacement. Okay. So there will be displacement in y and x direction. Here also same case, at each node 2 degree of freedom. Okay. Here also, so total degree of freedom is 8 in 4 nodes, at each node 2 degree of freedom, so 4 into 2 it is 8. So the next example of 2D element is quadrilateral element. Again there are 4 nodes for a quadrilateral, at each node 2 degree of freedom. So total degree of freedom for a quadrilateral element is equal to 8. Now we'll see what are the applications of two-dimensional element. So two-dimensional elements are generally used for analysis of plane trace, plane strain and plane bending. Okay. Shell structures are discretized using the shell element or curve element. So in case of one-dimensional element, the application, it is used for analysis of trusses and beam. Okay, so this was regarding one-dimensional and two-dimensional element. Okay. Then we'll see the these are some example of two-dimensional elements. Okay, 8-noded curve element. Then here plane bending element. So here 4 nodes are there, so at each node 3 degree of freedom, so degree of freedom is equal to 5, and the shell element. As we have seen the application of two-dimensional element, analysis of plane stress, plane strain problem, and plate bending. Shell structure are discretized using the shell element or curl element. So then we see the three-dimensional element. So the example is four-noded tetrahedron. Okay. So in three-dimensional, the degree of freedom at each node is 3. That is in x direction, y direction, and third one is in z direction. So here as the four nodes are there, at each node 3 degree of freedom. So total degree of freedom for a four-noded tetrahedron is 4. Then the next element, three-dimensional, is hexahedron. In hexahedron there are 8 nodes, and at each node there is 3 degree of freedom. So 8 into 3, so total degree of freedom is equal to 24. So application of the three-dimensional elements, three-dimensional, it is used for three-dimensional analysis of axis symmetric solids. Okay. So these are the application of three-dimensional element. So the question may be asked, explain the types of elements and their exam. Okay. So many times in exam this question has been asked in the university exam. So after seeing the types of element, we'll see the convergence requirement of a displacement function. So conversion is nothing but a representation of a point in x and y direction. Okay. So what is the first requirement? Displacement function must be continuous and compatible within the element. So it must be continuous. Continuous means what? The second element should start by taking the one is common of the first element. If you see here in the figure, you see, so this is one element, okay, and this is the another element. Okay. So this is the another element. So for both the element, so this is the common edge, and element 1 is starting after element, so element 2 is starting after element 1. So there is a common edge of the first element. So this is nothing but the continuous. That means displacement function must be continuous. Second, they have said that it should be compatible. Okay. So compatibles, these conditions occurs after the deformation. Okay. When the load is applied, it will deforms, and there should not be any discontinuity between the element. The element should not discontinue. Okay, means the element must not separate or overlap. The element should not separate. There should not be any sudden change in slope across the inter-element boundaries. Okay, so there should be not any drastic change in the slope across the inter-element boundaries. Third one is there, the displacement function must be capable of representing the constant strain state within the element. Okay, so how this can be achieved? This can be achieved by dividing the structure into smaller and smaller element. Okay, so here whatever the domain is given, that domain is to be divided into smaller and smaller part. Okay, so that the constant strain state is attained. Fourth one is the displacement function must be capable of representing the rigid body displacement. Okay, that is, when nodes are given such displacement under rigid body motion, element should not experience any strain and hence lead to the zero nodal force. Constant terms in polynomial ensure this condition. Okay, so these are the 4 convergent requirement of the displacement function. So in exam the question will ask like this: explain the convergent criteria in finite element method. And second question may be asked, state and explain the convergent requirement of displacement function. Okay, so after that So after seeing the conversion requirement, okay, we'll go. The next is, so we'll see the 2D and 3D Pascal triangle. So this is also very important topic in finite element method. Okay. So what is 2D and 3D Pascal triangle? So beside the convergence and compatibility requirement, one of the most important consideration in choosing the proper terms in the polynomial expansion is that the element should not be preferred, the element should have no preferred direction. Okay. So displacement shape which change in local coordinate. So this property is known as geometric isotropy or geometric invariance. Okay. So how this can be achieved? This can be achieved by using the Pascal triangle. Okay. So if we see in the figure, so this figure is nothing but it is a Pascal triangle. Okay. So this is the axis of the Pascal triangle. So for the first term it is 1. Okay. For linear term it is x and y. Okay. Then for the quadratic term it is x square xy y square. So how it is written? So here it is x square. Now here x square term is it is less and y term is added here, and here y square term is there. Okay. So for cubic terms there are 4 terms. Okay. X cube, x square y, x y square and y cube. Likewise for the 4th order terms the 5 terms are there. Okay. So this is the Pascal triangle. Okay. So when you are using these Pascal triangles, what you have to do? You have to maintain the axis of symmetry of a Pascal triangle. Okay. You have to maintain the axis of symmetry of the Pascal triangle. So for that what we will do? Select the element nearer to the axis of symmetry. Okay. If four values are to be selected, so how will you select it? 1, then x, y, and the third value will be xy you have to select. So that select the element nearer to the axis of the symmetry, so that axis symmetry of the Pascal triangle is maintained. Okay. So the Pascal triangle is always symmetrical. So the Pascal triangle is symmetrical. So this is a 2-dimensional Pascal triangle. Okay. So in exam the question will be explain the 2D and 3D Pascal triangle with example. Second question may be write a short note on Pascal triangle, geometric isotropy or geometric invariance. Okay. So this is the 3-dimensional Pascal triangles. Okay, constant terms. In linear terms, in 2D there were 2 terms, here there are 3 terms. Okay, next is quadratic, there are 6 terms. Okay, and in cubic there are 10 terms. So when we are writing the displacement field of a 3-dimensional element, in that case you have to use this 3D Pascal triangle. Okay, so thank you. So thank you for watching this video.